So we are talking about exponential growth, and now we're going to move on and discuss exponential decay. So, trying to draw a Cartesian axis here. XY axis, these are straight lines, even though they don't look straight. So, with growth, we always start at some A0, and our plot grows exponentially. We have this portion over here that we never really concern ourselves with because negative values of time don't really make a lot of sense. Well, exponential decay works in a similar way. If we have decay occurring, it will occur like this. I should put spaces between these. Dot this line, and then we get to like an initial condition, and decays exponentially down towards the asymptote of the x-axis. So the difference is, for decay, k is a negative number. And that's pretty much the only difference. We handle the problems in exactly the same way that we handled problems before. So you'll end up with a formula that's something like a of t equals our initial value e to the minus kt. So, similar looking relationship. And let's just jump into an example like we did before. This example, this is actually an actual example of a situation. Some researchers found traces of wood in some old in a site at a level that was determined to be ancient period. So it kind of indicated maybe there was an old forge there or something where they were cooking something. The wood contained 1.67% of the original carbon-14. Carbon-14 is an isotope of carbon. So it's a type of carbon, and we know that the half-life of carbon-14 is 5,730 years. That means that if you have a piece of carbon-14 that weighs a pound, in 5,730 years it'll weigh half a pound. So from this information we want to determine when the wood was burned. I'm going to put used here, when the wood was used, because it's of the unburned portions of the wood that they probably are taking the samples. So let's start with our equation. A of t equals A0 e to the minus kt. Or we can leave off this minus, and we'll take it into account when we figure out what k is. So our k will turn out to be a negative value if we do these calculations correctly. So, if we want to find out the time, how far back this was, the time that has elapsed, then we need to know what k is, which we don't currently know. We need to know something about A0, and we need to know something about A of t. Well, if we had A0, well, actually we do. We have a relationship. We found that according to our problem, that our final value of material, write this differently, we found that A of t was equal to 0.0167 of A0. So that's based on information in the problem that we contained 1.67% of the original. So we can then set this up as A of t over A0 equals 0.0167. And now our equation becomes 0.0167 equals essentially A of t over A0, and this is going to equal e to the kt. So still we're hunting for, so we've got, so this equals, just write it on this side too, 0.167. So we've got this relationship now to solve, but we don't know what k or t is. We want to solve for t, but we need to know what k is because otherwise we'll still have two unknowns in this equation. So how might we figure out what k is? So step one is, like we did before, we need to find k. So how do we go about doing that? Well, we can look at our problem again, and we find there's information here that says C14 in 5,730 years, half of it gets used up. Half-life. So that means that A of t equals A of 0 over 2, or 1/2 of A0. So A of t over A0 equals 1/2 now. And our other problems where we doubled, we had it equal to 2. So we can set up our relationship. A of t over A of 0 equals 1/2 equals e to the kt. So now we solve this. And for t now, we know that half of the material gets used up in 5,730 years. So k times 5,730. So how do we solve this? The same way we've been solving these problems up to this point. We're going to take the natural log of both sides. Natural log of 1/2 equals natural log of e to the k times 5,730 years. Now, this problem's in years, not hours, so we have to keep that in mind. Like the last problem. So now we have natural log of 1/2 equals, again, we've got natural log of e to something, which is going to equal k times 5,730. So k is going to equal the natural log of 1/2 over 5,730. If you do that calculation, you find out, since this is smaller than 1, it's going to be a negative number, 0.00, a very small number, 0, 1, 2, 0, 9, can actually move this over, 6, 8. Alright, we can take this now and go back to our original equation that we're trying to solve for the amount of time that has gone by based on the amount of carbon-14 left. We can figure out the amount of time that's gone by. So we have our 0.0167 0.0167. And we're about out of time here, but I'll just finish this up really quick. 0.0167. Again, remember that was equal to A of t, A of 0, A of t over A of 0. And this is going to equal e to the minus 0.000120968 times t. Now instead of looking for k up here, we're looking for t. We can do the same thing. Natural log of 0.167 equals minus 0.000120965 times t, not 6, times t. So therefore t equals 33,830 years. And that's where I'm going to stop this one.